Hi everyone. Uh, in last class we are discussing photochemistry part 2. In that part we are discussing quantum yield or quantum efficiency and some photochemical reactions and mechanism for photochemical reactions. In that initiation step, propagation step and transformation step and or termination step we are discussing, and examples of some photochemical reactions and the mechanism for some photochemical reactions and reactions between H2 and Cl2 and reactions between H2 and Br2 and high quantum yield or high quantum efficiency and low quantum yield or low quantum efficiency and photophysical process we are discussing in that part 2. So here photophysical process, this is nothing but here there is no chemical reactions in this photophysical process. There is no chemical reactions here. There is no chemical reaction by the absorption of light, but only the physical changes are occurring. For example, here A is a reactant molecule. It absorbs the light energy and it going to excited state and it going to excited state, and this excited state molecule will be deactivating this excited state molecule will be deactivated by the giving of energy, and it forms again the reactant molecule and it forms again the reactant molecule. So this is the process in physical states or physical photophysical process. So this process is called as photophysical process. So here it is because there is no chemical changes are happening, but only the physical process are occurring. So that's why this means the excited state molecule are converted to reactant molecule by giving out the energy which is observed. That's why that means the excited state molecules are converted into reactant molecules by giving out the energy which is observed. So that what is photophysical process. So here these photophysical process are explained through the Jablonski diagram. So the next we are discussing Jablonski diagram. So here A is a reactant molecule and it is this A, it is a ground state molecule, and this A is absorbing light energy and it is going to excited state. It is going to excited state, and as it is to excited state, again it will be returned to ground state by losing of the energy, and it is excited state, again it will be returned to the ground state by losing the energy or by giving out the energy. So here A is a reactant molecule, it absorbing light energy and it is going to A star. Now A star is a excited state molecule and it is losing the light energy, and again it forms the reactant molecule, that is A. So in the ground state many molecules are having many molecules are having electrons in paired up state. Electrons are in paired up state. So in the excited state, either it may be paired state or it may be unpaired state. In the excited state, either it may be paired state or may not be, or may be unpaired state. So that is explained through the spin multiplicity. That is explains through the spin multiplicity. Here the total state is given by 2s plus 1. The total state is given by 2s plus 1. So this is called as spin multiplicity. So here therefore the spin multiplicity is equals to 2s plus 1. Here s is equal to total spin of state. So here the next we are discussing electron pair. So in the electron pair, the paired up electrons in electron pair, in paired up electrons, so one electron will have positive spin and another electron will have negative spin. In electron pairs, one electron is having positive spin and another electron will have negative spin, so that the total spin S is equal to mod plus of plus minus of. S is equal to mod plus of plus minus of, that is equal to 0. So therefore the electron pair state in spin multiplicity, the electron pair in spin multiplicity is equal to 2 into 0 plus 1, that is equal to 1. So here the electron paired up energy states are called as singlet states. The electron paired up energy states are called as singlet state. So because a spin multiplicity is 1, because the spin multiplicity is 1, so these are called as singlet states. These are called as singlet state. So then next we are discussing unpaired electrons. So in unpaired electrons, so here the total spin, so S is equal to mod plus of is equal to 1, or S is equal to mod minus of is equal to 1. So whether it we can taken both are plus of or both are minus of, but the overall total spin is equal to 1, because we are using the mod value. We are using the mod value. So then the spin multiplicity is equals to 2 into 1 plus 1 is equal to 3. So here the unpaired energy states are called as triplet states. The unpaired energy states are called as triplet states because of the spin multiplicity is 3. Because of the spin multiplicity is 3. So these are called as triplet state. These are called as triplet state. So here generally in molecules the electrons are paired up in ground state. Generally in molecules the electrons are paired up in ground state level. Therefore always the molecules are existing in the singlet state or singlet ground state. So that is called as S naught. That is nothing but that is called as S naught. So the corresponding excited states means, here the corresponding excited state means the corresponding singlet excited state are S1 or S2, S3, S4, S5, S6 and goes on. And if you go for triplet states, there is no ground state. Generally we are observing triplet states, there is no ground state level for triplet state, because no molecules are existing in unpaired electron states. No molecules are existing in unpaired electron states, so that the ground state is not possible in case of triplet. So that the ground state is not possible in case of triplet, so that the triplet states will having only a excited states. because unpaired electrons would be there in excited states only. The unpaired electrons would be there in excited states only. So here the triplet states are T1, T2, T3, T4, T5, T6, like goes on. So there is no T naught, there is no T0 because triplets because the triplet states are not in ground state. In triplet states the ground state is not possible. So because all the molecules are in ground state in paired, because all the molecules are ground state in paired up electron states only, that is nothing but singlet state only. So here the energy of a singlet state is always higher than the energy of corresponding triplet state. The energy of singlet state is always higher than the energy of corresponding triplet states. That means uh, the energy of S1 is greater than energy of T1, and ES2 is greater than ET2, ES3 is greater than ET3, ES4 is greater than ET4, because in triplet states as electrons are in unpaired state, so there is a repulsion between two electrons. So there is a repulsion between two electrons, because as the electrons are having same spin, so there is a repulsion between those two electrons. So that's why the energy would be less than the energy would be less. So when compared to with the corresponding triplet state. So this is the diagram of Jablonski diagram. So here the ground state, or here S0 is the singlet state of ground state. So here this is S0, this is a singlet state of ground state, and here S1 is the first excited singlet state, and S2 is the second excited singlet state, and S3 is the third excited singlet state, and here the T1 is the first excited triplet state, and T2 is the second excited triplet state, and T3 is the third excited triplet state, and goes on. So here the energy of S1 would be more than energy of T1. Here the energy of S1 would be more than the energy of T1, and the energy of S2 would be more than the energy of T2, and energy of S2 would be more than the energy of T2, and the energy of S3 would be more than the energy of T3. So here the molecule is absorbing energy, so that it absorbs the energy and will be excited to either S1 or S2 or S3 or S4. So that depends upon the how much energy that we are giving to the molecule. That depends upon the how much energy that we are giving to the molecule. So the molecule it absorbing the energy in the ground state, that is nothing but in the singlet ground state, and it will be excited to singlet excited states, that may be S1 or S2 or S3 or S4. So after that, in this example we are considering that molecule absorbing the energy. After that in this example we are considering that molecule absorbing the energy and it is going to S2 state, and it is going to S2 state. So after going to S2 state, it maybe goes to triplet state, or it maybe goes to S1 state. After S2 state, after going to S2 state, it maybe goes to T2 state, or it maybe goes to S1 state. So this is, as it is going to S1, that is called as interconversion or internal conversion. So because of all these are S0, S1, S2, S3, S4, so here all are singlet states. So that means there is no change in spin multiplicity. There is no change in spin multiplicity. All are having, so here all are having same spin multiplicity. So that is called as interconversion or internal conversion. So if it is goes to T2, for example, if it is goes to T2 and from T2 to S1 or S1 to T1, so these are called as ISC, interstate crossing. These are called as ISC, interstate crossing, because there is a spin multiplicity. There is a spin multiplicity changes from S2 to T2 or T2 to S1 or S1 to T1. So this is called as interstate crossing. So here the radiative process from S1 to S0. Here the radiative process from S1 to S0. So the molecule in first singlet state, it is going to singlet ground state. The molecule in first singlet state, it is going to singlet ground state, and it gives some energy, so that is called as fluorescence. So the radiative, so here the radiative transformation between S1 to S0 is called as fluorescence. So here the possibility of transformation takes place from S1 to T1 through ISC, and after getting the molecule in triplet excited state, that is first triplet excited state, that is nothing but T1. So it may be going to ground state, it may be goes to ground states, that is S0. So here the radiative transformation between T1 to S0, the radiative transformation between T1 to S0, that is called as phosphorescence. So here the excited molecule reaches from higher energy state to lower energy state. Here the excited state molecule reaches from higher energy states to lower energy state without change in spin multiplicity. That is called as interconversion or internal conversion. So this is indicated by IC. So here example S3 to S2 or S2 to S1 or S1 to S0. So here the emission of radiation through S1 to S0 transformation is called fluorescence. Here the emission of radiation through S1 to S0 transformation is called as fluorescence. So here the transformation from higher energy state to lower energy state, the transformation from higher energy state to lower energy state with the change in spin multiplicity, with the change in spin multiplicity is called as interstate crossing or ISC. This is called as interstate crossing or ISC. So here the example T2 to S1 or T1 to S0, and here the emission of radiation, here the emission of radiation through T1 to S0, emission of radiation through T1 to S0 transformation is called phosphorescence. Emission of radiation through T1 to S0 transformation is called as phosphorescence. So in this case, the fluorescence and phosphorescence, here the observed energy is greater than emission energy. Here the observed energy is greater than emission energy, and the observed frequency is greater than emission frequency, and the absorption or observed wavelength is less than emission wavelength. In the case of fluorescence and phosphorescence, the observed energy is greater than emission energy, observed frequency is greater than emission frequency, but the observed wavelength is less than emission wavelength. So in the case of fluorescence and phosphorescence, the observed energy is always higher than the emission energy. In the case of fluorescence and phosphorescence, the observed energy is always higher than, always greater than the emission energy. For example, if it is observed 100% of energy, 100% of energy, and we may get 99 or 99.5 energy only. So we may not get 100% energy. So here in the case of resonance fluorescence, in the case of resonance fluorescence, the absorption energy is almost equals to emission of energy. In the case of resonance fluorescence, the absorption energy is almost equals to emission energy, and the absorption frequency is always equals to, the absorption frequency is almost equals to emission frequency, and the absorption wavelength is almost equals to emission wavelength. Absorption wavelength is almost equals to emission wavelength. So it means whatever the energy which is absorbed by the molecule, the same energy will be getting out. It means the energy which is absorbed by the molecule, the same energy will be getting out the while coming out the ground state. So that's what that is called as resonance fluorescence. So here next we are discussing fluorescence. So the definition of fluorescence is the radiative transformation between from the first singlet state, from the first singlet excited state to singlet ground state is called as fluorescence. So here the radiative transformation between the first singlet excited state to singlet ground state, that is nothing but S1 to S0, is called as fluorescence. So here the absorption of light and the emission of light. Here the absorption of light and the emission of light occur almost so here the absorption of light and the emission of light occur almost simultaneously, so that is called fluorescence. So here the emission of frequency less than emission of the emission of frequency is less than absorption of frequency. So here the fluorescence is exhibited by the substances in dilute solutions. Fluorescence is exhibited by the substances in dilute solutions. So that is the molecule coming from first excited state. The molecule coming from first excited state S1 to singlet ground state by giving out the energy. So here what kind of molecules shows the fluorescence? So here the molecules with rigid structure. So here the molecules with rigid structure shows the fluorescence. So for example, the molecules with multiple bonds, like N double bond O, N double bond N, C double bond O, and C triple bond N, C triple bond C. So here those molecules will exhibit the fluorescence. And here CaF2 and uranium are also exhibit the fluorescence. And some of other examples like benzene, benzoquinone, pyridine are also exhibit the fluorescence. And fluorescein and azophenanthrene are also exhibit the fluorescence. So the next we are discussing phosphorescence. So here the radiative transformation between from T1 to S0. The radiative transformation between from T1 to S0, that is triplet excited state to singlet ground state. The radiative transformation between from triplet excited state to singlet ground state, that is called as phosphorescence. So here the emission of light radiation, on a longer time scale, this is a longer time scale, not simultaneously, is called as phosphorescence. So the emission is continuous even after excitation cases. So that here that emission may converted the emission may continued for second or minutes, hours and days based on the circumstances and based on the materials which are observed. For example, the molecules shows fluorescence. The molecules will shows fluorescence dissolved in boric acid H3BO3 or glycerol and shows phosphorescence, and also zinc sulfide as well as sulfide are second A group elements. So these are also shows phosphorescence. So then next we are discussing photosensitized reactions. Here generally in photochemical reactions, any one of the reactant molecule, generally in photochemical reactions, any one of the reactant molecule is absorbs the light radiation or light energy. Any reactant molecule will absorb the light radiation or light energy, so that it is getting excited state, so that the active species are formed, so that it getting the excited state and it forms active species. So these active species are react with other reactant molecule, and finally it forms a products. These active species are react with other reactant molecules, and finally it forms a products. So here, to occur a photochemical reaction, the basic point here, it is the one of the reactant molecule should absorb the light energy. One of the reactant molecule should absorb the light energy. So without absorbing the light energy, there is no photochemical reaction. Without absorbing the light energy, there is no photochemical reaction. For example, here in some cases, if whatever the reactant molecules are there in a reaction, whether it may be 2R, 3R, maybe 5 or 10. So if it is those are unable to absorb the energy, but those are having to undergo for photochemical reaction. So all the reactant molecules which are there in a system, so are unable to absorb the light energy, but they having to undergo a photochemical reactions. So what happening? So here no reactant molecule absorbing. So in some cases, what is happening, if it is not possible, an external molecule absorbs the light radiation and transfers to the reaction system, so that photochemical reactions takes place. So this kind of external substances or external substance, this kind of external substance which are absorbing the light energy is called as photosensitizer. This kind of external substance which are absorbing the light energy is called as photosensitizer. So this type of reactions are called as photosensitized reactions. This type of reactions are called as photosensitized reactions. So the major work of photosensitizer, it may not involving the reaction. The major work of photosensitizer is it may not involving the reaction, but it absorbs the light energy. It absorbs the light energy and giving to the reactant molecule. So generally the photosensitizer is not involving the reaction, but it absorbs the light energy, and these photosensitizer the light energy giving to the reactant molecule, so that the reactant molecule will excited in the reaction and the reaction would be processed. So the photochemical reaction would be takes place. So this is the work for or work of photosensitizer. So for example, we see the photosynthesis reaction. So in this photosynthesis reaction, so 6CO2 react with 6H2O in presence of chlorophyll and light, and it forms carbohydrates. So here 6CO2 react with 6H2O in presence of chlorophyll as well as light, and it forms carbohydrates. So in this reaction, chlorophyll is acting as a photosensitizer. In this reaction, chlorophyll is acting as a photosensitizer. So in this reaction, CO2 and H2O are unable to absorb the light energy. In this reaction, CO2 and H2O are unable to absorb the light energy. So now this chlorophyll will takes the energy, and this will give to the energy to the reactant molecules, so that the reaction will be processed, and finally it forms the products. And we see the another example. So here mercury, cadmium, zinc, and benzophenon, chlorophyll, and SO3. So these type of molecules are acting as a photosensitizer in different reactions. So here mercury, cadmium, zinc, benzophenon, chlorophyll, and SO3, those molecules are acting as a photosensitizer in different kind of reactions. So here in photosensitized reactions, the photosensitizer is referred to as a donor. In photosensitized reactions, the photosensitized is referred to as a donor, and the reactant molecule are called as acceptor. Here photosensitizer referred to as donor, the reactant molecule are called as acceptor, because in photosensitizer is absorbing, the photosensitizer is absorbing the energy, and it is giving to the reactant molecule, and it is giving to the reactant molecule. It means it donating the energy, it donating the energy to the reactant molecule. So that's why photosensitizer is called as donor, and reactant molecule is called as acceptor. So the next the mechanism of photosensitized reactions. So here D1 absorbing the light, and here D1 is a donor, or D dash is a donor or photosensitizer or ground state molecule, which is absorbs the light energy, and it forms singlet excited state molecule, and these singlet excited state molecule react in presence of ISC, and it forms a triplet excited state molecule, that is D3. And here D3 next step, in next step D3 is the donor, gives the energy to A. Here A is the reactant molecule, that's nothing but acceptor. So here D3 react with A, and it forms 3A reactant triplet state plus D, and the reactant triplet state molecule 3A undergoing for reaction, and finally it forms a products. So this is the reaction mechanism of photosensitized reaction. So here donor is in triplet excited state, donor is in triplet excited state, will transforming the energy to acceptor reactant molecules. Donor is in triplet excited state, and this donor gives the energy to acceptor reactant molecules, and so that the reactant molecule will be going to triplet excited state, triplet excited state, so that uh, the triplet excited state molecule undergoing for reaction, and it finally it forms products. So here D is taking the absorbing energy and giving to the reactant molecules. That's why what is the role of photosensitizer in the photosensitization reactions. So here examples of photosensitizing reactions. So first, dissociation of H2. So here the hydrogen molecules are directly will not absorb the light energy. Here hydrogen molecules are directly will not absorb the light energy. Here in this reaction mercury will absorb the light energy. Here in this reaction the mercury will absorbing the light energy and it will be going to excited state. Mercury will absorbing the light energy and it will going to excited state, that is active species. So the next, the excited state molecule mercury react with hydrogen and it forms, here the hydrogen will be going to excited state. So this is the excited state hydrogen, and this excited hydrogen undergoing the dissociation and it forms hydrogen radicals. So in this reaction finally it forms hydrogen radicals. So in this reaction here the mercury is acting as a photosensitizer. Mercury is acting as a photosensitizer. So then next, decomposition of ethylene. Decomposition of ethylene C2H4. So in this reaction mercury absorbing the light. Mercury is absorbing the light energy and it is going to excited state. So here Hg star is a excited state molecule, and here C2H4 ethylene is a reactant molecule. This C2H4 react with excited state molecule and it forms C2H4, and here C2H4 is a excited state molecule, and this C2H4 excited state molecule undergoing dissociation to form C2H2 and H2. So in this reaction mercury is acting as a photosensitizer. So the next two we are discussing chemiluminescence. In this chapter next we are discussing chemiluminescence. That means here the production of light radiation. It means the production of light radiation through a chemical reaction. So in photochemistry we have what learned in is absorbing some light energy. In generally in photochemistry we have what learned in is by observing the some light energy. Some chemical reactions are takes place. So that's what is photochemistry. So here the light energy radiation is produced. The light energy radiation is produced through a chemical reaction, that is called as chemiluminescence. The light energy radiation is produced through a chemical reaction, that is called as chemiluminescence. So because of some chemical reactions light is produced. In some chemical reaction light is produced. So this process is called as chemiluminescence. So these are the reversible to the photochemical reactions. So these chemiluminescence reactions are reversible to photochemical reactions. So here the light produced is called as cold light. Here the light produced is called as cold light. So for example, glow of fireflies, that is nothing but glowworms. Glow of fireflies, that is nothing but glowworms in which become leucine protein, in which become of luciferin protein. Luciferin protein, some light is evolved. So here green glow of slowly oxidizing phosphorus. So this is the chemiluminescence. So here in this chapter, in this photochemistry topic, we are discussing these things we have discussed. So here in this chapter, mainly photochemical reactions and what is the process of photochemical reactions, that is primary process and secondary process, and how to the photochemical reactions are takes place, and after that laws of photochemistry, those are first law, that is nothing but Grother's Draper's law, and second law, that is Stark-Einstein's law, and the next quantum yield or quantum efficiency, and examples of high and low quantum efficiency, and the next photophysical process, and this photophysical process explains through the Jablonski diagram with the fluorescence and phosphorescence, and the next photosensitized reactions, and next chemiluminescence. So these are the major things in the in that we have discussed in photochemistry chapter.